still took seconds, right? But if you actually think about how long it takes to sweep up the garbage from a star and get rid of the jets, it's on the scale of a month, not on the scale of seconds. So you have to come up with other mechanisms. So there are two mechanisms that people like to have as their favorite. So I underline the theoretical model. On the theoretical model, they're going to have a black hole forming, and while it's forming, it's going to have two jets back to back, and these jets are going to have internal shocks and external shocks. So it's going to be a complicated engine by the time you actually try to write it. So the long gamma reverse, we think a very massive star in this red night phase and goes through a core collapse, and it does that. A black hole forms in the center, and the jets punch their way out. I'll show you a movie about this later on. Now, what about the short one? Well, like I said, if you're trying to disrupt a star and suck into a black hole, that takes too long. So you got to start with more compact objects. So you can think about trying to suck a white dwarf into a black hole, and that still takes too long. You could then think about two neutron stars, two compact stars, like a neutron star and a black hole, or co-orbiting about each other. And then can you, when they inspire, and they collapse and form a black hole, and make a relatively jet and die away in something on the scale of a second. That's the issue that's involved here. And this is a picture to remind you of this beautiful theoretical model and the real of the data. That's what the thing is. And you can then make theoretical models of two neutron stars inspiring, where these neutron stars have their own spin and magnetic field, and they're going to come together and try to disrupt it. And you've got to not only organize the matter, but you have to organize the magnetic field. You have to organize the magnetic field. So here's a mess of the matter trying to come together. And you're forming a black hole in the center, you've got all this garbage around it. And somehow in the center you've got to get the black hole, the magnetic field organized into a jet-like structure, and everything happens. And if you read the scale here, this is 7 thousandths of a second, 14 thousandths of a second, 26 thousandths of a second. So you have to do this all in a tiny fraction of a second. Okay, so that's cool. I have a little movie. I'm running out of time, but I'll show it to you because it's fun. One of the NASA has this after this movie. So, you know, this is all the world beginning saying on average, it's about one detected per day. So you have a statistics problem. There are probably several days that, you know, efficiency factor and everything else, and you can only detect about one. And this is the jet coming out and punching through the material. And if we had more time, I would show you data where you can see the decay, you can actually see ripples in the decay. And that the star wobbling around is actually punching through layers. So here's an increasing kind of this black hole. Oh, sorry, this is one that I'm supernova. This is a neutron star. So the whole point of this is that you have to do simulations to prove you can get a neutron star together. You have to do more careful simulations to prove you can get the two neutron stars together and the magnetic field organized, and that you can then get it all set up. And that's what this whole movie is about. This is showing you can make it explode. That is, you can merge them. And so if you watch the time frame on 7 milliseconds. So the first question is, can you make the black hole? Second, can you sweep the stuff up? And then can you organize it so the magnetic field make you have a jet? So this is a messy kind of problem. Those of us that work in the cosmic microwave background, we like the linearity and the simplicity of it. This is you know, horrible magnetohydrodynamics. So this is a big advertisement for the computer. So this was designed because they show you the mass in one color and the magnetic field in the other color. So you can see the mass here and the magnetic field there. And they've got to both organize themselves in basically a fraction of a second. So somehow the black hole is here. And the magnetic field here is super strong. And so here you're seeing the pictures of one after the, you know, sequentially that I showed you in the chart before. And somehow they do manage to organize themselves in such a way as to make a jet. Okay, so let's compare that to how complicated punching your way through the supernova, and then there's the material that was probably ejected by the supernova before that makes the external shock. So you see a series of the X-rays, the gamma rays, the X-rays. You then see additional X-rays and ultraviolet, and then eventually you see other shocks. And so in the end, what you see is something that's like this. It's a fourth star sitting there, and then suddenly this relative jet comes out, and this relative jet can have a gamma factor which is anywhere from 100 to a few hundred, and eventually it's bringing some additional material. And you don't know whether it's accelerating material that's picked up along the way, or this is something that's happening in the core. You just don't know what's going on in that situation. What you see is the jet, and you see the afterglow left over from the shock, or the supernova itself left over behind, right? And then eventually it looks like a crash. So in this picture, we're saying here's a very massive star. It goes through its burning very quickly until it gets to the iron in the core. The iron can't burn anymore. Energetically, it's not favorable. It let it pass to a black hole. You get the jet, and then you punch through the star, and that's what you get. And you expect to see this in the star-forming region. So here's the thing in the star-forming region, and here's the take set of jets to see what's going on. But you can imagine what it would be like if you lived in the neighborhood. It would not be cool to be on the planet where the supernova, where the gamma ray burst went off. So this is the whole planet in flames on one side of the gamma ray burst, because instead of getting 30,000 in an area like that, you're getting R-squared factor much better. So it turns out there's a really cool game you can get. I recommend this highly. It's called Animal Armageddon. It has the 7 different ways you can kill all life on Earth, right? And one of the things that it has, besides the asteroids coming in and supernovas going off nearby, is the gamma ray burst trying the Earth. And so you can go through that. And in fact, they say one of the things, there was a time period where this was the dominant form of life, which was a giant myeloid, and it's quite huge, and it's living long and running, ruling the world. And then some event happened, roughly 488, 443 years ago. 70% of all sea life died. So being in the ocean didn't protect you from the gamma ray burst enough. You just got kind of wiped out. So we got to worry about flying the Earth. We got to be worried about all those deaths in the sky. So we got asteroids and gamma ray burst and everything else. Luckily, we have other things to think about. So as John was saying, we're wondering about what happens between the times we see the cosmic microwave background release. We go through the dark ages, and then the first stars of the galaxy begin to form. The first stars light up, and eventually we think that their spheres of ionization get large enough that the universe becomes ionized, so that by the time the universe is 7 years old, the universe is fully ionized. And how do we probe this area? Right? Well, you build GWST, but you also need something to point your map out. So there are several different ways people propose to do that. JWST, but you need something to tell you where to point it. Another thing is trying to use it for the 21 centimeter line, and it turns out you just don't have big enough telescopes to get redshift for things in this area very well. So you have to think about other ways. And we have a theoretical model going on where we're getting the framework of the cold dark matter or the warm dark matter, whichever you prefer. We're getting this network put together, and we're thinking these guys are going to actually be linked. There's going to be some things going on. You know whether the first stars at a redshift of 15 or 30, but somewhere in here you're going to get the first stars for the galaxy forming. And that's the same period where you think you can begin to see people over do that. So